Unlike the addition property for inequalities, the multiplication property for inequalities comes with a warning. Or maybe I should just call it an observation, but it is something we have to be careful about. Here's an inequality statement that we know to be true. 3 is less than 5. 3 is clearly a smaller number than 5, so this is a true statement. Here's another one. -3 is less than 5. Well, any negative number is going to be smaller than any positive number, so we know this is true as well. -5 is less than -3, although the absolute value of -5 is bigger than the absolute value of -3. In other words, this number is farther away from 0 on the number line than this number is. It's because it's farther away in the negative direction that it's smaller than -3. So this is also a true statement. If I multiply both sides of all three of these inequalities by 2, then this is what happens. For my first inequality, the left-hand side becomes 2 times 3 is 6, and on the right-hand side, 5 times 2 is 10. 6 is still smaller than 10. For my second one, 2 times -3 is -6. 5 times 2 is 10, and any negative number is still smaller than any positive number. So this inequality is still true. For my last one, I get -10 and -6. And although -10 is bigger in absolute value than -6, it's farther to the left on the number line, so it's also still smaller than -6. Watch what happens, though, when I multiply both sides by -2. Here are my three original inequalities multiplied by 2. If I change the 2 to a -2, and perform those multiplications, -2 times 3 is -6. 5 times -2 is -10. Which is smaller, -6 or -10? Actually, it's -10, because -10 is farther to the left on the number line. So -10 is smaller than -6, or -6 is greater than -10. For my second problem, multiplying -2 times -3 gives me +6. 5 times -2 gives me -10. Any negative number is going to be smaller than any positive number, or a positive is always bigger than a negative. The last one, I have -2 times -5 is +10, and -3 times -2 is +6. Which one's smaller? Well, it's the 6. 10 is bigger than 6. The only thing that's different is that instead of multiplying by +2 on both sides, I multiplied by -2 on both sides. And in fact, although the numbers are the same, the signs are different. And, most importantly, the inequality symbols are going the opposite direction than they were in the counterpart problems. What's the rule here then? You can multiply both sides of an inequality by anything you like. But if the number you choose is negative, it's going to have the effect of flipping over the inequality symbol. Okay, now that we understand that, let's take a look at our first example. Solve the inequality 3a is greater than or equal to 15. Well, I'm allowed to multiply or divide both sides of my inequality by the same number. I'm going to choose to divide by 3 because 3 divided by 3 is 1. So I get a on the left-hand side, 5 on the right-hand side, and I'm just going to drop the sign straight down. As I begin to do this, I think back Did I multiply or divide by a negative number? No, it was a positive number. So I don't need to flip my sign, it literally just gets copied down in the same way that an equal sign would. My solution is A is greater than or equal to 5. Solve the inequality, negative 3t is less than 18. I can proceed as though this was an equation, noting that the thing that's stuck to my variable is negative 3 and that it's stuck there by multiplication. Undoing that is going to mean dividing by the thing that's stuck to the variable, negative 3. Negative 3 divided by itself, in fact, any number divided by itself, is 1, times t, and 18 divided by negative 3 is negative 6. I'm going to bring down my inequality symbol, but as I start to write it, I think back. Did I divide or multiply by a negative number? Yes, I did. So I can't quite just copy down my symbol. I have to flip it over. Instead of a less than, I have a greater than. Or you can think of it as pointing in the opposite direction. The solution to this inequality is t is greater than negative 6. It doesn't matter what sign this side of the inequality has. Here's another problem that's very similar to the one we just did. Solving this inequality means unlocking or unsticking the number that's stuck to the x. What I do on one side, I must do on the other side. So my left-hand side is 1x, or x. My right-hand side is positive 4. That's not what affects whether or not I flip my sign. That's affected by this right here, or actually, this right here. Did I multiply or divide by a negative number? Yes, I did. So I have to flip my sign over so that it's pointing in the opposite direction. If the sign you start with contains an or equal to line, then your answer will include an or equal to line as well. If the sign you start with does not include an or equal to line, neither will your answer. This is example 5 in your textbook from page 209. The way it's written, negative x over 4, makes it a little bit difficult to work with. Some of you may be comfortable with the idea of just multiplying both sides of this inequality by 4 to clear the denominator, and that's fine. But I'd like to take a look at breaking up the left-hand side a little bit, or writing it another way anyway. If I wanted to, I could think of x over 4 as 1 over 4 times x over 1. In other words, if I were given this multiplication of fractions, then I would have 1 times x, which is x, over 4 times 1, which is 4. So if I can do this multiplication and end up with x over 4, then I can rewrite x over 4 as a multiplication problem. Now, I don't need to write x over 1. I can just write x. So whenever I see t over 7, I can think 1/7 t. Or y over 19, I can think 1/19 y. X over 4 is 1 over 4 x. I hope you noticed throughout that all I was talking about was the x over 4. I'd already brought down the leading negative. The only piece I was breaking up was the fraction. The fraction is a negative number, so this expression is also negative. All I've done is rewrite the left-hand side of my inequality. I'll copy down the rest of it, and then I can look at this as negative 1/4 times x. So to solve this inequality, I want to multiply both sides by the number that's going to give me a 1 when I multiply them together. This times negative 1/4 needs to be 1. Whatever that number is, when I multiply it on the left, I will also need to multiply it on the right. What number times negative 1/4 equals positive 1? Well, it's going to have to be negative because I need a negative times a negative to give me a positive. And to get 1, I need the reciprocal of 1/4. 4 over 1 times 1 over 4 is 4 over 4, or 1. So the number I've ended up multiplying is negative 4. Therefore, I have to do it on the right-hand side as well. My left-hand side is now 1x. My right-hand side is now negative 8. 2 times negative 4 is negative 8. But I've multiplied by a negative number. Therefore, when I bring down my sign, I have to flip it over. Instead of pointing to the right, it's going to point to the left. The solution to this inequality is x is less than negative 8. Another way to have done this problem, negative x over 4 is greater than 2, would be to multiply both sides by 4 to clear the denominator. 4 can be written as 4 over 1. 4 times x is 4x. 1 times 4 is 4. This is currently a positive times a negative is a negative. Now I haven't multiplied by a negative here yet, so I end up with negative x is greater than 8. I don't want negative x, I want positive x. So I can think of either dividing both sides by negative 1 or multiplying both sides by negative 1. The left-hand side now is x, the right-hand side now is negative 8. But I multiplied by negative 1. So rather than just dropping my sign down, I need to flip it over so it's pointing in the opposite direction. That's the same problem as I did a minute ago, with a slightly different approach. Use whichever one works for you.